So our lesson today, we're going to spend some more time on electron configurations. We introduced this idea of electron configurations in grade 11, but we're going to add a lot more to it today and add some more rules and deal with some of the exceptions that you'll run into. So hopefully you remember a little bit from grade 11, and if you don't remember too much, we'll go over everything that we learned first anyways. So when you hear the term electron configuration, it's essentially replacing our model of the atom that we used up until quantum theory. So if you remember your Bohr-Rutherford model of the atom with the circles and the orbits and the electrons, that was a model of the atom based on those theories. The electron configuration is going to do the same thing. It's going to show how the electrons are arranged among the different orbitals that are present, but now we're going to refer to our SPDF orbitals, their suborbitals, and the actual electron arrangement that are there. So what we're going to do is learn a few different types of representations. We're going to learn first about the rules, and then we're going to learn the new representations, orbital diagrams, energy level diagrams, and then we'll do a good review of your um, typical SPDF notation configurations that we learned in grade 11 and throw in some new exceptions. So first rule, you would have learned about this rule in grade 11. This is the Aufbau principle. And the Aufbau principle says when you're filling up any type of electron configuration, the electrons go in the orbital with the lowest energy first, and you fill that up, and then you move on to the next lowest energy, an energy level and orbital until it's full, and then you move on to the next one. The whole purpose of doing this is to try and minimize the energy that the atom has or stabilize it. So whenever you see the term minimize energy, we want to think it's going to stabilize or make the atom its most stable arrangement. Now there's two ways of looking at the Aufbau principle. One is with that diagonal rule, and the other one is looking at the periodic table approach. Both work, but knowing how the periodic table is arranged by orbitals can help you figure out the Aufbau principle really easily, and it's a lot more useful, especially in grade 12, with a lot of the other rules and some of the exceptions that we'll see. So still your choice, as long as you can answer the question correctly, that's fine. But I would suggest trying the periodic table method. In either case, let's review both. So if you're going to use the zigzag method, this is the little diagram that you can use that'll help you figure out the order for filling. So you do the orbitals 1 to 7 down in one column, and you'll have these for the s orbitals. Then for p's, they go from 2 to 6. D's go from 3 to 6, and F's are only 4 and 5. So you need to line them up nicely. You don't want to be sloppy with this diagram. They need to be lined up in nice columns and then also in nice rows. Once you do that, you draw on these diagonal lines, hence sometimes called the diagonal rule. So what you do with this one, when you draw your arrow across, it'll go diagonally through all of these orbitals and so on. Then you're going to follow the arrows from end to tip to figure out the order of filling up the orbitals. And the order is going to be from lowest energy to highest energy. So down here to follow along, we've got the list here. Lowest energy starting with 1s, and highest energy, it goes past 4p. I've just got those ones listed there. So you start up at this point on the arrow, move your way through, and once you go through an orbital, that's the one you fill up first. So 1s is up here, which is why we're going to fill up 1s first. Once you fill that up, you have to backtrack and start at the next arrow, and always follow in the same direction, end to tip. That way you pass through 2s. So 2s down here is the next lowest orbital that needs to be filled. And you do the same thing. 2p, 3s, so 2p, 3s. Go back up here, 3p, 4s. Then we keep going, 3d, 4p, 5s. And you would keep going on and on and on. Now, why does this matter? After 4s, the order from lowest energy to highest energy does not follow energy level. You can see it goes 1, 2, 3, 4, and then all of a sudden it jumps back down to 3. So it will kind of alternate between a couple of different energy levels in terms of ones that are lower or higher in energy. So after that point, it's not that easy to predict. If you want to take another approach, the periodic table method is really helpful. So what you have to remember for this method, if you're going to use it for your electron configurations, is to make sure that you know where the orbital blocks are. S's are in your alkali and alkaline earth metals over here. Your P block is over here in the representative elements. D block are transition elements. And then your F block are your lanthanides and actinides. The only other thing you need to remember with this method is where the energy levels start with the orbitals. So S starts at 1, P starts at 2, D starts at 3, and F starts at 4. It's not too hard to figure out if you remember S, P, D, F in that order. 1, 2, 3, 4. So it will tell you where those orbitals and the energy levels that they start in. To use this method, you just follow along by atomic number. So up here you have hydrogen. The first energy level that we go through is 1 and S, so that's hydrogen. And then we go through helium, so we fill up 1s first. Then we keep going. Number 3 and number 4 are lithium and beryllium. That means you get in the 2s orbital. Then if you keep following by atomic number, boron all the way over to neon, 5 to 10, 2p. Then you keep going, sodium, magnesium, 3s. Then you keep going, aluminum all the way to argon, 3p. And you can see how this is pretty easy as long as you have your periodic table and follow the numbers. Then you can figure out the order. So next is potassium and calcium in 4s. And then here you can start to see where it's going to switch. So the next one is 3D, and then 4p, and so on. One thing that's also really helpful when you're using this method is you can see where the lanthanides and actinides come in. This is one of the most common ways to see the periodic table with the lanthanides and actinides, the F block pulled out of the periodic table and put down below. But if you actually follow along the periodic table, they fit in actually in this section here. So if you look on your periodic table, cesium is 55 and then barium is 56. If you were just to continue horizontally and go into this 5D block, you would see it's number 71, lutetium. You don't count 56 to 71, you have to go 56 and then 57. Where's 57? Well, it's down here. So this row here will continue here. You have to move all the way through it and then rejoin it up here. For francium and radium, this block down here continues here, 87, 88, and then you go down into 89, 90, and so on. So we don't deal with too many that are that big, but that's one spot where you need to watch the order. The other advantage of using the periodic table to figure out the order for filling orbitals, it also tells you how many electrons go in each orbital type. So if you look at S block, there's one column, two column. It's 2 columns wide, so it fits 2 electrons maximum, and then you're out of the S block. If you count D block elements, and if you have your periodic table count across, going across from here to here in that transition block is 10 columns or 10 elements wide. We know that that is going to correspond to 10 electrons in the d orbitals. That's how many can fit in d orbitals. Do the same thing for p's. If you count across here, there are 6 elements or 6 columns lined up, which means 6 electrons. And if you do the same thing down here with the F block, there are 14 elements across, which mean they can hold 14 electrons. And all you need to do is just count. So it saves you a lot of memorizing time. If you remember the general organization of the periodic table, it can really make a big difference in problem solving and understanding the arrangement of the electrons rather than just relying on that zigzag diagram and having to know a lot more info there. So now what we're going to do is introduce 2 other rules which are new that apply to electron configurations. So the first one's called the Pauli exclusion principle. It says only 2 electrons can occupy the same orbital. So we've talked about 2 going in each orbital or suborbital, depending on which orbital type you have. And when the 2 electrons are in there, they have to have opposite spins. So remember that ms number that we talked about in the first lesson for our quantum numbers, magnetic spin number, 1 electron's positive 1/2 and 1 is negative 1/2. So they're spinning in opposite directions with the same magnitude. If you were to tie this in with quantum numbers, what it means is each electron has its own unique set of 4 quantum numbers. If you were to try and isolate the quantum numbers for each electron that are paired up, they would have their own unique set of numbers. It's kind of like your address or your student number. Everyone has their own little code attached to them. Each electron has their own code or set of numbers assigned by the quantum numbers. When we get into a couple of examples next, we'll try and tie in this theory so you can see how it works. Next rule is called Hund's rule. Hund's rule says electrons in the same orbital will not pair up until the orbital is half filled. So this part of the rule is kind of like what you might have done when taking public transit, or maybe even now more pronounced with the ideas of social distancing. So electrons don't want to buddy up and get close to one another unless they absolutely have to. You get on the bus, you sit by yourself. More people come on the bus. If there's available seats, they're probably going to go and sit by themselves rather than sit right next to you on the bench or on a seat that's right beside you if there's more space to spread out. Electrons want space, so they will sit by themselves until the orbitals are half filled, and then if they have to pair up, then they will pair up after that. The other part of Hund's rule says when the electrons are unpaired, they must have the same spin, up or down. Generally, when you're filling up orbitals, the notation is to give them a spin up or an upwards direction followed by down. So we'll see that come up next in our diagrams. So I've got a picture of the periodic table on here just for reference if we need to come back to it when we're doing some of our practice problems. But if you don't have one handy out yet, then I would definitely suggest having one handy because looking at these orbital diagrams and energy level diagrams and electron configurations, having this handy will make your life a lot easier. Okay, so now what we're going to do is look at orbital diagrams. Depending on which textbook or reference you look at, some will use boxes or circles or even lines to represent each orbital and suborbital. I prefer just a simple method with lines because it's a lot less cluttered, but you'll see a few different representations as you get into some practice or learn more about this topic. How you arrange them is they're horizontally and you put them by increasing energy. So we're going to do a simple example with Nitrogen. So nitrogen we know has 7 electrons. What is the first orbital that we have to fill? That's going to be 1s. So we draw a line and we're going to write 1s under it. The s orbital can only fit 2 electrons, and there's only one orbital shape. So we only need one line. One line is going to hold 2 electrons. So that's the first orbital that we will need to fill. Then we go on to our next orbital. The next orbital to be filled would be 2s. So same thing, since it's still an s orbital, we're going to put a line and 2 electrons can go in there. The next orbital that would be filled up would be 2p. Now, how many suborbitals are in 2p? There are 3 suborbitals. So we're going to draw 3 lines. 1, 2, 3. And we're going to write 2p under it. So this one could be for 2p on the x-axis, on the y-axis, and then on the z-axis. If you don't remember how to get this order, you either go to your diagonal rule or the periodic table. So if we go back and take a look, this is where nitrogen is. It's number 7 on the periodic table, 7 electrons. To get there, we have to go through 1s, we have to go through 2s, and then in here, we're in the 2p block. 1, 2, 3 electrons in. So now we're going to fill the orbital diagrams. This order here first, before we start filling, this is following Aufbau principle. Lowest energy to highest energy. So why do we learn about these rules? This is where it's starting to get tied in. So lowest energy to highest energy is our filling order. Next, we're going to follow both Hund's rule and Pauli exclusion principle at the same time. So we start to put electrons in. Electrons are going to be represented by a half arrow. This would represent 1 electron. According to Aufbau principle, I have to fill up the lowest energy orbitals first before going on to the next ones. So if I'm going to do that, I need to fill up 1s first. One goes spin up, and then the other one spins down. This is showing you both Hund's rule and Pauli exclusion principle. Only 2 electrons in the same orbital, and they have to have opposite spins. Hund's rule says the electrons aren't going to pair up until it's half filled. So for S, when we put 1 in, it's half filled. Then the electron goes the other direction, and it's going to pair up. First electron spins up, second electron spins down. Then we keep going on to the next one, 2s. Same thing, put 1 in, it's half filled, spin up first, then I'm going to put it downwards to pair it up, spin down. This is full. Now I go on to my next orbital. I have 3 more electrons to go. So here, Hund's rule will become more apparent. Electrons in the same orbital will not pair up until the orbital is half filled. So I have to put these in half filled first and then pair up as needed. So I've got 3 more. 1, 2, 3. Now I have 7 electrons and I've done my configuration for nitrogen. Hund's rule says I have to put them by themselves or half fill it up until the orbital's half filled, which it is, but I don't have any more electrons to go in. They're all unpaired and all pointing in the same direction. Let's say I had 1 more electron if I was doing the next element, which would be oxygen, 8 electrons. Once this is filled, the next electron would go and fill up that first suborbital, and then they would go in and pair up like this as needed. But We don't need that for nitrogen because it only has 7 electrons there. And that's what an orbital diagram looks like. Horizontal, fill up the orbitals, pair them up as they fill up, and half fill them and then continue filling them as needed. Let's try another type of diagram. Energy level diagram, very similar to an orbital diagram. The only difference is you're going to do it vertically and you're going to show how the energy increases vertically. So you need a scale. You're going to put energy here. It doesn't have to be anything crazy. And then we're going to do the same thing. What's the first energy level that gets filled up? It's 1s. I'm going to put 1, 2 electrons in. The next one is 2s. 1, 2. And what you'll find with these diagrams is they stagger the orbitals. So they'll line up all the s's, and then the p's, and then the d's, and f's if you actually got that far. So if I'm going to do p's, it needs to be higher than 2s. And I'm just going to put it a little bit off to the side here. 1, 2, 3. So you can see the order for filling the energy level diagrams and arrangement is exactly the same as orbital diagram, but this one is vertical. If I had more orbitals to fill, I would just continue on. The next one would be 3s, and then I would have 3p, and I would fill them accordingly. But for this one, I don't need any more, so I don't need to put any in, and you don't even need to show any more orbitals past this. Finally, we're going to do a quick review and give you some practice of expanded and condensed electron configurations. So what happens with these ones? These ones are going to show your energy level, number, orbital letter, and total number of electrons in each suborbital. The disadvantage with these ones compared to orbital diagrams or energy level diagrams are you don't see how the electrons are distributed. So since this is something from grade 11, if you think you can do these configurations, why don't you pause the video and see if you can get the answers on your own, and then we'll go through and check. If you think you need a quick review, I'm going to move the slides back to that periodic table that was in there before, and we're going to take a look just at silicon so we can go through that one, and then you'll be able to try the others out. So if you think you need a review on how to write electron configurations, we'll walk through the one with silicon together, and hopefully that'll jog your memory. So silicon sits here. Silicon is number 14. So in my electron configuration, I need 14 electrons. So if I'm using the periodic table, I'm going to follow from number 1 all the way down to 14. I have to go in order. 1, 2, 3, 4, 5, and so on. So I'm going to start here and drive my car. My car goes through 1s. This is 1s and 1s. So I would write down 1s. How many elements have I passed through? 1, 2. That means 2 electrons. So I put my 2 there. Next one, 2s. How many have I gone through? 1, 2. Then I go through here. I'm in 2p. How many electrons? 1, 2, 3, 4, 5, 6. I'm not at silicon yet. I have to end at 14. So I go through 11 and 12. Next one, 3s. 1, 2 electrons. And then this is the 3p block. How many electrons am I going in? 1, 2. So that would be the answer for the electron configuration for silicon. So if you want to try some of the others that are listed there with your practice, give them a shot. If you're ready to check, I'll show the answers now, and then we'll do a little bit more with electron configurations next. So these are the answers for the other configurations. Just to give you a little bit more of a taste of the order for filling, cesium is quite long, but it'll test you and see whether you know how to fill your orbitals with the right number of electrons. Now, if you're looking at things like selenium and cesium, they're not very practical. They're big, long electron configurations. They're kind of cluttered or busy to look at. So to get around the fact that electron configurations, um, while useful, can also be a little bit overwhelming, there's another version that are a little bit more helpful, especially for the ones with more electrons. If you remember from last year, there's also condensed electron configurations. So these ones can be simplified by representing a set of filled orbitals using a noble gas. So if we have something like rubidium, the normal expanded electron configuration looks like it is here. But if we put it in shorthand form is shown with krypton and then 5s1. So how does that work? If you go to your periodic table, find where rubidium is, and go backwards until you find the previous noble gas that comes before it. You should find that krypton comes before rubidium. Rubidium is number 37. Krypton is number 6. So this is the noble gas prior to your element. So prior to rubidium in this case. Everything up to that point is completely filled. If you remember, noble gases are stable and full and happy. So all of those orbitals and their electrons are completely filled and stable. So instead of writing them all out, which is what you see here in red, we just put square brackets around that noble gas and say, hey, I've got all of these orbitals. They're full and stable. After that, we've got whatever orbitals are not filled. So anything that comes after krypton still has to be put in your diagram. And this is where knowing the periodic table arrangement can be really helpful, because you can just continue on from there. So in this case, there's only one orbital, which is 5s1, that comes after, and that's where rubidium lands. So it's a lot better than writing out this big long configuration. You can just write the shorthand one. And to be honest, where all of the action happens is usually with your valence electrons. That's where all the chemistry is and chemical properties and where bonding happens, anything like that. So that's where you want to focus your attention anyways. Now there's a little bit more in terms of electron configurations that wouldn't have been covered in grade 11. And these are some exceptions. So we're going over a couple. There are more on the periodic table. These are just a few, and these are a few that are a little bit more logical based on our knowledge. But if you're looking at different electron configurations, especially if you have your detailed periodic table with you, where it shows you all of the configurations on the periodic table, if you skim and scan through, you're going to find that there are some exceptions scattered throughout. So let's look at one together, and then I'll let you take a look at another. So chromium. So first find where chromium is on your periodic table. Chromium is in the middle in the transition block. Underneath chromium, another element that also follows the same pattern will be molybdenum. So this one will also have a slightly modified electron configuration. When you write the electron configuration for chromium, based on what we've learned, up here where it says expected, this is what I would have thought you would have remembered to do. So you count chromium, and you would think it ends in 3d4. But when they've studied this particular element, the electron configuration ends in 4s1 and 3d5, not 4s2 and 3d4. So why does this happen? If we take a look, this is the expected configuration just with the last two orbitals. This one's for chromium here. So looking at this, this is what you might expect to see. But why does it actually end in 4s1 and 3d5? When we take a look, you'll see that up here we've got a full orbital, and this is a partially filled orbital. The one that's observed shows a half-filled orbital here with the S, and this one down here with 3D is also half-filled. So what happens is this electron here jumps ship and it says, I'm going to move over here. Remember Hund's rule says electrons like to be unpaired before they pair up? Part of that has to do with stability. Two electrons in the same space, they're both negatively charged particles. Why would they want to be close together? They're going to repel. So since there's that one empty seat on the 3D bus in that 3D orbital, that electron says, forget it, I'm getting off the 4s bus and I'm moving to the 3D bus. So it moves over, and what you see being observed is a half orbital here and a half orbital here. Half-filled orbitals are more stable. Up here, this is a partially filled orbital. It's not horribly unstable, but if that electron is able to move over and add one more there, that half-filled arrangement is slightly more stable. There are some other places where you will see some exceptions. So if you go back and look on your periodic table, find copper, and two other elements under copper are silver and gold. They will also follow this arrangement as well. If we look at these two, normally you would expect they would end in 3D9. It's not all the way at the end of the D block, but what's observed here is you get 4s1 and 3d10. So here, one of the electrons from 4s jumps and completely fills up the d orbital this time. In the examples with chromium that we just looked at, it made two half-filled orbitals. But here, you've got a 4s1 that's half-filled, and this one is completely filled. A completely filled orbital is also very stable. It's symmetrical. The electrons can be evenly distributed, so it's also very stable. So when you're looking at elements and finding that there are some exceptions, these 5 here are ones that you should be aware of. Copper, chromium, molybdenum, silver, and gold. You might notice there might be similar kinds of patterns with elements that are outside of the transition block. They do not follow these exceptions. You'll find the exceptions in the transition block or sometimes in the F block, but not anywhere else. Part of your discussion board over the next couple weeks will be to investigate some of these exceptions and tie them in with some more periodic trends. So hopefully you'll be able to look into this a little bit more. All right, so last up, just to make sure that you've understood some of the concepts from the lesson, here are 4 practice problems for you to try. So what I would recommend is pausing the video, and we'll have a look at the answers for the first 3. The last one there is just for some extra practice if you want, but we'll look at the first three answers together. So if you haven't tried them as of yet, pause them, and I'll give you a quick overview of the answers next. All right, so here are some of the answers. First up here, drawing an orbital diagram for sulfur. So lowest energy to highest energy, half filled to completely filled. Here in the P block, put them in half filled, and then one more to start pairing up. Number 2, your energy level diagram looks similar to orbital diagrams, but it is vertical. So for potassium, potassium has 19 electrons. So we start at 1s, then 2s. Make sure 2p is higher than 2s. Make sure 3s and 3p are also slightly different in energy level. That's really important to note with this one. Last over here, what happens if you have an electron configuration for an ion? An ion, you either add or subtract electrons. So if you run into any questions with that, negatively charged ions, make sure you add electrons so that one extra electron is shown in here. So hopefully that helps do a good review of electron configurations and learn a little bit more about quantum theory. So just practice away and let me know if you have any questions.